Hello everyone and welcome, and by everyone I mean Eric and John. Welcome to a bonus session. I went through the modules 1 through 6, talked about deliverables 1 through 7. So now I thought I'd circle back and talk a little bit about some of the things we did early on that dealt with the graphs and graph processing. So I thought I would do so by presenting it from a different perspective, in particular that of Spark and using Databricks as a way of doing Spark. As a reminder, this is relevant because things like Spark allow you to do data analysis and machine learning at scale, meaning across considerable volumes of data. So one of the things that Spark does support is the concept of graph processing. So I thought I'd spend a little bit of time talking about what that means. Go ahead and start the video in case somebody joins. What that means and how we do it, right? So how do we do graph processing in Spark and Databricks in particular? So as a reminder, as we've talked about in the past, when we talk about a mathematical graph, we talk about things made up of nodes and edges, or vertices and edges. The basic idea is that you have something, a vertices, V1, which is a point essentially, and you have something that goes from it, an edge, to another point, V2. Also, graphs can have cycles. They can go to themselves directly, so you can have an edge that goes from V1 back to V1, as well as one that goes from V2 back to V1, creating a longer cycle. And so those are the key concepts. Generally speaking, both vertice and edge have things like a name. They may also have additional attributes associated with them as well. So there's a free book out there, if you're so inclined, that talks about discrete mathematics and algorithms, and it's a pretty good resource. You may want to take a look at the address, so cusack.hope.edu /notes, and then instructor, or then / instructor equals books, and one of those is the latest version of it's essentially in PDF form, and it'll download relatively quickly, and it's a pretty good resource. Talks a good bit about it. Sometimes there's a gap in our knowledge, and discrete math is one that I've seen sometimes being a gap, in particular when we get into things like graph theory, which is what we're talking about here. And this goes into very formalism of what it means of vertices, a set of vertices, a set of edges between those vertices, and so on. So something to consider if you're at all unfamiliar with discrete math, because sometimes it shows up even though you are a data scientist. So I'll ignore my error because I'm trying to get a sparse matrix to work, and it's giving me some grief. So why do you use a graph processing system versus just use something like a relational database to store it, or in this case a data frame potentially? And the idea is that there's some algorithms out there that are optimized for it. What we'll talk about here is some of the things that are built into what's called graph frames. But sometimes you want to do things like calculate the longest path, the shortest path, maybe the least expensive path, which is taking into consideration not just the distance, but also the weights associated with the traversal of a given edge from one node to another. So you could sum up those various weights and come up with a cost of taking one path over another. And sometimes it may be counterintuitive that less expensive edges is better than one expensive edge. You can think about that in terms of logistics, if you will. Maybe you're plotting driving from one city to another, and perhaps between two cities the only way to get across there is a toll road. So the cost of traversal of that road becomes much higher than just the cost of the fuel of the vehicle. So sometimes graphs also make it easy to see things, clusters and hotspots, and edges that are very problematic. So to talk about it, there's this concept of graph frames. So what's a graph frame? And it's basically a combination of two or three things. it's a combination of GraphX, which is a set of libraries associated with graph processing, with Spark data frames. Data frames inside of Spark are similar to something like pandas, except they're intended to be processed across a cluster in a resilient way, so that if for some reason the cluster were to terminate, the data is not necessarily lost, or at least a node in a cluster were to terminate, you won't necessarily lose everything. You can create a graph frame by basically combining together a set of nodes and a set of edges. So yes, my computer just died right before this, so I think Windows has figured out something bad happened. Which is ironic, right? It's right before the presentation whenever it decides to go down. So to construct a set of vertices, I have some tables out here that I previously imported data into named Vertices, original name, I know. And there's also going to be one called Edges. So the basic idea is to be able to do a select from it, and we can see the example we're doing here is that oftentimes whenever you're taking classes at especially undergraduate level and sometimes even graduate level, you have prerequisites that you have to satisfy before you can take those courses. The idea is that the proper information is made available to you or demanded of you after you have the foundational elements in place to support it, right? So what I've done is converted a subset of a particular program into a set of dependencies. So there's classes, in this case are the vertices or nodes. The edges are the prerequisites between them. And so this is basically retrieving the vertices. The next step is to go through and rename them. So one of the unique things with inside of graph frames is that it has to have an ID. It looks at the name of the column as ID. In this case, I previously called it node. I'm renaming it, and that's what this is saying, is take the data frame that I have and rename node to ID. And so doing so, we can now see that I have an ID column. A similar sort of concept, I select E from edges. So basically there's a table out there called edges, corresponds to essentially a CSV of edges that I imported. These are the arcs between nodes, right, essentially, or vertices. So from an ID to an ID with a certain type of relationship, in this case prerequisite. You could potentially have other types of relationships, but for now that is an attribute that is associated with that edge. So that's what I'm talking about here, is that I need to rename the edges from and source. From turns into source, and to turns into destination. So it's essentially changing the names of those attributes using, again, the from with column. And you notice I'm chaining these together, and then I'm taking the result of that and applying it back to itself. Very similar to what you might do in pandas. So here we can see the thing along the way. So I'm going to go ahead, and so that we make sure that this is going well, I'm going to go ahead and run these commands so we can see them running. In this case, it's actually sending the job out to the cluster and running it and getting back the response. And so I'm just stepping through these. And really we're not doing much here other than kind of just seeing it. So that's what display is making it actually happen. If we didn't have this display in here, it would just basically be constructing what's basically the plan of how it's going to do the work, but it wouldn't necessarily do it. So the next step is to actually, we just ran this, that's right now, is to take those two data frames that I've constructed. One of them as the source and destination in a relationship, the edges called E, and another is the vertices, V, so the nodes that we're connecting together. And you basically just simply say import from graph frames, everything in this case, and you construct a new graph frame by passing in the vertices and the edges, and it returns back to you a graph frame object. You still have access to those data frames inside of it, so it's kind of like a container. It nests them together, so you can access .edges, that was what was passed into the E, and you can also access .vertices, which was passed in as the V. And so we can still see the vertices, which are the nodes, and then the edges between those nodes. So going on a step further, we can actually kind of plot this out, so and make it so you can see it. And that's what this is doing. Not the strongest plot that you'll ever see, but it's basically going through and constructing a set of lines and so on between the 2 points in a spiral rotation sort of thing, so that it's easier to see what's going on, and drawing the arrows so that you can see the direction of them. It's kind of hard to see on some, but it starts from a wide and goes to a smaller, so you can see the node name pointing at the particular items. Similar visualization coming out of Neo4j. Neo4j is a graph database. Desktop application is what I used here. It's a pretty cool tool, but wasn't necessarily wanting to show it. But this is basically the query that returns back pretty much 25 of the nodes that have edges between them. So we're seeing kind of the names in a little cleaner, prettier way. Same information is up here. It's just that here you have to go to the trouble of looking up what is number 11 and so on. So it's a little less convenient. You can do the same thing going in and scrolling to the vertices. Number 11 is the capstone number 1, ITS 438, and 12 is capstone 2, 439. Not surprisingly, 11 and 12. 12 has something pointing at it, lots of stuff pointing at 11. So this is kind of the last one in the chain if you're a software developer. You can also see it a little cleaner here, but it's the same basic information. So there's several algorithms that are available to you inside of the graph frames. One of them is a triangle. So the basic idea is there's a set of nodes that are involved in some sort of a relationship. So we can kind of see it if we kind of pick it together. The node number, say 16, is involved in a triangle. So we're saying here, give me back the ones that have the triangle count that has more than 0. So one or more that are involved in one or more triangles. So if we take a look up here at 16, we should be able to see that there is indeed a triangle here, right? So it's basically that sort of thing. It doesn't necessarily depend upon the direction of the arc. It just means that it's one of the ones involved in it. It's kind of a way of looking at a relationship within essentially kind of like a neighborhood of the graph. The same thing is the in degrees. This lets us know how many things are pointing at a given item and order them in decreasing fashion, right? So capstone number 1 has 7 things pointing at it in this set of data, and that's what this query here is doing. Is we're basically saying, for the graph, give me back the in degrees, and so that I can read it better, join that information to the vertice name so we can actually see what the vertices is or are, and then order it by the descending amount of the in degree that we just calculated. And that's what this shows you here, is that the capstone 1 has the highest number of things pointing at it, and followed by, in this case, interconnected network devices is secondary. Out degree, the opposite way. Who points at the most stuff? In this case, Introduction to Object-Oriented Programming is foundational for a lot of different courses. Not too surprising, right? You need to know how to do OO programming before you do a lot of other stuff. And this is a similar query. We're basically saying, on the graph, give me the out degrees, take that result, join it with the vertices based upon ID, so that we can actually see the pretty name here versus just the number. And I'll name and label as well, and type. So all this stuff is coming in that join. Total number of edges, this is basically the summation, right? So the degrees, the total number of edges in or out of a given node. Not surprising, capstone 1 is the highest with 8, 7 pointing at it, it pointing at 1, capstone 2. So there's several graph algorithms. These are pretty well known algorithms, and as such they've been implemented in GraphX and are available to you in graph frames. You do have to have a checkpoint, a folder inside of Spark. It's basically a place where it has to write, so it can't create it because it's already there. We set it as the checkpoint, and then we basically do some things like figure out the things that are connected to other things, right? And so this is a pretty important idea. Is it's essentially showing you if there are disconnected elements inside of a given graph, and that would be important, especially in this scenario, because why would you take a course that doesn't either require you to take something else or enables you to take something else as well, right? And it could be that it's an indication that there's a link missing. Could be a valid scenario, but it'd be worth taking a look at. So there are several of these that are together and all have something to do with each other, and so those are kind of important. You can also do the kind of a grouping together to see which ones are the first and so on, so the largest numbers. You may also want to do some filtering so that you can take a look at those things where there is exactly one inside of it. That kind of gives you some indication. Group by components is kind of could be important to know. And there's also several isolated nodes. So if there are, oftentimes you may want to remove them. So removing the isolated nodes just shows you the ones that are connected to something else in the graph. So they don't. An isolated node is a node that doesn't have any edges to or from it, right? So it could be worth getting rid of depending upon what's going on. If you think about it in terms of a common scenario for using graphs, is things like page rank of web pages. So in that situation, having a page that has nothing pointing at it or it points at nothing isn't all that important whenever you're talking about a search result based upon popularity, which is what PageRank is about. So an important thing to do is potentially to remove those that don't have anything to do with it, because it simplifies the amount of processing you have to do. You also have this concept of strongly connected components, and it's a graph theory concept that basically every vertice is reachable from every other vertice. In this particular case, I don't think we have any because we don't have any real cycles, right? So you would have strongly connected, I guess we do. Oh, that's interesting. Strongly connected, in this case, it must be ignoring the relationship between them. No, that's right. There are no strongly connected ones because there's only one item in every one of these strongly connected groups. Sometimes you want to try to find something inside of a graph, and so you apply the concept of searching, and you have the choice of doing a breadth first search, which is kind of what you would think it is based upon a background in computer science. It's going to look across first rather than trying to go deep, so it's going to go in a fashion that is trying to find it using without going through a whole lot of hops is the basic idea. PageRank is what made Google initially, right? And originally it was called Google PageRank. That was the algorithm, still kind of is. And what it does is figures out how important things are by how many things are pointing at them, and in turn how many things are pointing at those, and so on. So the idea was to get around the concept of creating a bunch of fake pages pointing at your page that you're trying to get people on, so that it has a high degree, n degree, right, a lot of things pointing at it, but it really has no value because the things that are pointing at it aren't important. And that's what PageRank attempts to address. It's a common, very common graph algorithm that you'll see. In this case, you can see that whenever we apply PageRank, not surprisingly, Capstone 1 is really important because a lot of things point at it, and it has a lot of things that are pointing at it. In turn, Capstone 2 is the second most important thing, primarily because Capstone 1 points at it. And so you can basically see that's how it works. And PageRank is an iterative process. It runs until you reach either kind of a tolerance, or you exhaust the number of iterations that you're going to let it run. In this case, it ran really quickly because it's a small graph, right? If it was a larger graph, it could take longer to do. And so here we're taking a look at the weights between the various edges. In this case, the weight is from 1, which is going to be the most important, to not so important, which is smaller. So it's a way of essentially associating how important a given page or edge might be in your graph. Label propagation algorithms is around essentially sharing information amongst a neighbor. So it's a way of potentially converging. It doesn't necessarily guarantee conversion of things in the same community show up, and community being things that are kind of related to each other. It's built in, so in this case we're changing it to the label to class name, right? So just to make it a little cleaner as to what label means. And then we can see here the things converge here to these things are kind of together, in the sense that they're all 2, right? It's that you essentially are clustering in a way together, and it's not exactly clustering, but you're lumping together those things that have relationships between each other that are essentially a neighborhood. Motif finding speaks to the concept of being able to find patterns or kind of structure within a graph. And in particular, the most common thing you're going to want to look for is things that maybe are cycles. So if you check for a loop that involves 2 nodes, so A points at B and then B points back to A, is something that may or may not be desirable. It certainly would not be desirable in a course catalog perspective, right? That means that it's kind of a chicken and egg problem. You have to take class A before you can take class B, but class B is also a prerequisite for A, so that would be very undesirable. So we can do the search, and not surprisingly we don't find any, which is what you would hope for. This is the syntax that is used whenever you're doing the search. This is the vertex you're looking at. This is the relationship between it. And these are just kind of placeholders. It doesn't really equate to anything other than you're uniquely saying that this is a different relationship than this. And then this is the name of the nodes, essentially placeholders that you can do. You can also check for a loop of 3 nodes. So maybe A points to B, B points to C, C points back to A. Would also be undesirable, right? Because it implies the cycle that exists inside of it. You can also look for just the things where essentially something is necessary for another. So a chain that contains 2 vertices, there's going to be quite a few of those, right? In this particular case, pretty much anywhere that there's a prerequisite, it's going to be the list of them. So there's 26 prerequisites, and that's likely also the count of our edges. So it is a data frame. So that's a key concept, is that what we get back from the result, so chain 2, is a data frame unto itself. So we can do things that we do to data frames, such as doing some aliasing of columns. We can do things where we can make it certainly prettier than what you're seeing up here. We can do selection of things that we care about. So a.name. So this is essentially a JSON sort of structure, right? And we're pulling out of at a and then .name. So we'll get this value out. Pretty handy stuff. So you can make it pretty, right, and also give it an alias as well, so that it looks better than that mess up here, this is useful from a diagnostic perspective, but this is not very human readable. This is much more readable. And you're seeing here the prerequisite, the class that is the prerequisite for another prerequisite, right? So this is a prerequisite for this, just as this is for this. So pretty useful stuff. We can then look for a chain of 3, right? So similar concept of you have to take A before you can take B, which is required for C. So here we can see there are 16 such chains of 3 long, and we can print those out, just not necessarily doing all the relabeling, but this time we're just doing a select off of the data frame. And so you can see the ones that start showing up, and you'll start seeing that capstone is going to show up in a lot of them, right? So that's a pretty interesting kind of observations. Take it a step further. Here what we're kind of working towards is what's the longest chain, because sometimes that's important, especially if you're figuring out what classes to recommend to incoming freshmen. So you want to take the prerequisite that is the most important, or the one that is necessary to unlock the most classes later on, earliest. So now we're down to 9. There are 9 chains, and if we take a look at what those look like, you have to take these 9 courses in order to get each other. Obviously, you see where I'm going. We're going up to 5, so there's a chain of 5 different nodes in this graph. So then you can see there are only 4 of those that are 5 long. If we take a look at 6, you'll find there are none with 6, right? So probably an important thing if you start figuring out how long it takes to get through a program is what is the longest chain. So as you might say in casual speak, what is the longest straw, right? So you'd want to tackle those first, the thing that unlocks the most classes later on. So if we take a look back at this, the one that is 5 vertices, and they end with capstone 2, it's not surprising it's the same number, 4, because capstone 2 is the capstone. It's the last course you would take in the program. So we take a look at what that looks like. Then you can start figuring out what classes are probably important to take in the first as soon as you can, right? And what, if any, is the relationship between them. And you can also start seeing some things here that show you that this is kind of an important class too, as is that, and as obviously is that. So these 4 classes are necessary to be in the longest chain. So that's an overview of graph processing in general. Now moving on to something where we talked about in the past, which are pizza example, and attempting to use this to do Monte Carlo. That was my original intent, is, okay, we got a graph, right? And we have, not Monte Carlo, Markov processes. We have a graph in both situations, so maybe we can do something here. And not surprising, or maybe it is surprising, it's kind of harder than it looks. So if we start off, we basically can construct a graph of, we've got a pizza V, so vertices, pizza A, edges, and then we can construct a graph from that, and then we can plot that graph. Not the most exciting, doesn't have the arrowheads, but it kind of does give you a sense that there's 4 and there's connection between these 4 stages. We can take a look at the vertices. So pizza graph.vertices, and those are familiar, right? Wait, order, get, and then leave. So those are the various sort of names of those, and then we have our edges between those states. So you go from wait to wait, 50% chance, wait to order, 30%, wait to leave, 20%, and so on. So the basic information in a set of edges, right? So then we can construct a graph and basically print everything out of those vertices. So the same sort of thing. And we can plot it in a prettier way, somewhat prettier. And so here we can actually see the edges, right? So you wait, and you order, or you leave, or you get your food. You get your food, you either wait or leave, and so on. So you can see the direction of the arrows in this plot. A little challenging to put the weights on this same line because it gets kind of ugly. But again, these are the probabilities and the self loop here is the hard part, right? There's a 50% chance that if you're waiting, you'll continue to wait. And the same thing over here. If you leave, you're probably going to stay gone, 90% chance. There's a 1% chance that you'll come back in, or 10% chance you come back in and wait again. So that's what that's showing you. And then we can take a look at the edges between them as well by taking a look at the graph edges. We can make sure, or we can just get the ones where there are loops. So source is equal to destination. And that's the wait and the leave, right, which we talked about. So wait to wait is 50% chance, wait to leave 90% chance. So doing a check, because with Markov processes we expect it to come up to 1 whenever we're talking about sources. So when you go from a source to something else, those all should add up to 1, which they do. So you can actually do the graph processing inside of graph frames to do a Markov process. I tried to figure out how to do it. Can't really do it because it really kind of wasn't intended to do that. The closest I was able to get is there's this concept of message passing inside of graphs, where an edge can essentially send a message to those that it points to, or those that are pointing at it can send a message to their parent or the originator of the edge, and so on. But I couldn't come up with a way to turn that into something that does Markov processing. Might be able to do it. I couldn't figure out how. And it seems like it's kind of a limitation. In this particular case, things like PageRank don't really mean a whole lot, right? Because it's not going to help you much, because this isn't about weights of it necessarily. It's more about the kind of the overall result. So the way to do that is to essentially turn it into a matrix. So we start by constructing a weighted matrix of essentially going through creating some index sizers. So we basically are turning labels into an index, and we're making sure that they're alphabet, right, descending. The reason being, if you don't do that, your edges and the names of your IDs and your edges will be different than those in your vertices, and you want them to be the same, so that one is pointing to one being pointed to is the same thing as the one that's being pointed to, right, and so on. So your destination index and source index, this is weight to weight is 0 to 0 now. Weight to order is the destination is 1, the source is 0, so it's lining up. Weight is 0, to leave is 2, and so on. So we basically have just turned the strings into numbers. Then we can, and I'm just showing you that same mapping of what that's the decoder ring. 0 is weight, 1 is order, 2 is leave, 3 is get, as in get the food, and making sure that there are no tricks up my sleeves. The same thing is true when we're talking about source and destination. So it is lining up. So then we can basically create our transition matrix, and this is a little hunky. We start off, we set the matrix to be a NumPy 0, 0 matrix of size vertice by vertice, vertice count by vertice count, because we are dealing with a square matrix. Then we go through and essentially we set it to 0 initially, then we override that value with things that are at a certain source and a certain destination, and then we give it the weight associated with it, which is the probability. So the end result of that is that we end up with a matrix, and we can take a look at that matrix, and it should look familiar. It is the state transition matrix. The rows should add up to 1, which they do. Then it's as simple as basically just doing the NumPy, raising it to a power, and the results are what we would expect. This is where I was working on it and trying to turn it into a sparse matrix. It didn't work out yet. So it's the intent there is to kind of prove out that you don't necessarily have to have those zeros, that you only, the point of a sparse matrix is all these values here that are just zeros wouldn't be present, wouldn't be stored essentially. And the reason you do that, it's not so much this case because it's about half and half, right? There's half the values and half are 0. But if you have something where the data is mostly zeros and just a few data points, memory gets very expensive to store it in that form. So what you do is only store those values that are present, and then you have operations such as multiplying matrices that can be done across sparse matrices versus a dense matrix, which is what we've got here. That's what I was working on here. Working through it, not quite finished, but it's likely to get there. This is where I was playing with trying to do message passing. The closest thing I could get is essentially aggregating the sum of the messages being sent out. So of the ones that are pointing at something, do they all add up to 1? And that was proved to be true. So with that, I'll go ahead and wrap this up. This is again, Databricks doing graph theory and doing things like Markov processes, which we talked about in Unit 2, and potentially doing so at scale. So think about it if you are a retailer or something where you're modeling a huge number of states with a huge number of possible transitions. You could do that in this sort of environment across huge amounts of information. Leveraging the concepts of a data frame that is distributed across a cluster in combination with graph algorithms, or potentially just doing it in NumPy, again distributed across a cluster. So with that, if you have any questions about the material, let me know. If there's something you'd like me to talk about on Thursday, let me know that as well. I'd be glad to focus on whatever it is that provides the greatest value. As always, stay safe, and I'll talk with you soon.